The next talk is by Shaojie Zhuo from Qualcomm. And the topic is an empirical study of low-precision quantization for tinyML.
Good afternoon, everyone. My name is Shaojie Zhuo, and today I will present our work, an empirical study of low-precision quantization for tinyML. This is a joint work with Hongyu from University of Toronto and other team members in Qualcomm AI Research. tinyML aims at deploying machine learning models to embedded devices with ultra-low power consumption. However, those embedded devices are often highly resource-constrained with limited memory and computation capability. It's challenging to design and deploy a neural network model with good accuracy while meeting the strict memory, latency, and power requirements. Quantization is one of the widely adopted model compression techniques. It compresses a model by using low-bit precision representation for parameters and activation tensors, and it can greatly reduce memory usage and computation of a model. As an example here, quantizing a model to 4-bit can make its memory usage half and computation only 1/4 compared to an 8-bit model, and quantizing a model to 2-bit can save the memory and the computation further. In this study, we focus on benchmarking post-training quantization for tinyML models. We are interested in the layer-wise optimization paradigm as shown in this figure. It takes a pre-trained full precision model and a small amount of calibration data as input and optimize the quantized model in a layer-wise manner with the help of the full precision model. It shows promising results on low-precision quantization. Particularly, we investigate and benchmark recent publications in this paradigm, namely AdaQuant, AdaRun, BrackQ, and BitSplit, to show their performance on low-precision quantization on tinyML models and reveal the key ingredients of the recent progress on PDQ through different ablation studies. We implement a quantization simulation framework for fair comparisons among different algorithms. In the framework, we use simulated quantization to quantize a tensor and then dequantize it back to floating precision to simulate quantization loss, while the computation is still performed in full precision. For example, the input and the weights of this convolution layer go through the quantizer to introduce quantization loss, and then go through the rest of the original convolution computation to generate the final output. We adopt the linear quantization scheme that the quantization function is determined by the quantization parameter scale and the zero, which is related to the bit width. We use per-channel symmetric quantization for parameters and per-tensor asymmetric quantization for activations to balance computation and accuracy of a model. With the quantization simulation framework, we construct a unified PDQ pipeline that takes a pre-trained full precision model and a set of calibration data as input and produce the optimized low-precision model through 4 sequential steps: the full precision model preprocessing, quantizer insertion and initialization, quantization optimization, and low-precision model post-processing. Then, existing PDQ algorithms can be deconstructed and fitted into the pipeline as assembling different options in each step. Here I show the CLE pipeline, AdaQuant pipeline, and AdaRun pipeline. We can see that existing work usually focuses on improvements of specific steps without considering the whole pipeline. With the whole pipeline in mind, we can do ablations to reveal the best choice by varying options in each step, and later we can use the best option to construct the optimized PTQ pipeline. To illustrate the options in each step, for preprocessing, we have cross-layer equalization and outlier channel splitting to preprocess the full precision model to redistribute the parameters of the model and make it more quantization friendly. For quantizer initialization, the quantization parameter can be determined based on the min-max value of the tensor or by minimizing the mean square error between the quantized version of the tensor and the full precision one. For quantization optimization, there are different variables can be optimized in the quantization function to minimize the layer-wise loss, including the quantization parameter, the full precision weights, the rounding function, or directly optimize the bits in the integer space. And there are options for the optimization granularity, whether the loss is minimized in a layer-wise manner or block-wise manner. For post-processing, there are bias correction and bias tuning that optimize the bias of the model to minimize local loss or end-to-end loss. Now, with all options for different steps, we do ablations to show their performance differences. We select a variety of tinyML models for different use cases to do the benchmark. They are mostly compact models performing classification tasks. We train the model based on the recommended setting to achieve comparable accuracy for each model. The top one accuracy and other statistics of the model is listed in this table. This slide shows ablation on quantizer initialization using different methods. The x-axis is the bit width and the y-axis is accuracy of the model. We can see that the cyan line here, which is the MSE-based initialization for both weights and activation tensors, performs the best, while the red line, which is the min-max-based initialization, is usually sensitive to outliers and performs worst. For the preprocessing with or without cross-layer equalization, the solid line with cross-layer equalization seems effective for 3-bit quantization, while it has negative impacts on the accuracy for 4-bit quantization. For different optimization variables, they perform similarly for high precision quantization, but for lower precision quantization, there's big discrepancy. Optimized rounding and optimized bits, the cyan line and blue line here, usually performs better than the other two. This is because different parameterization have different optimization difficulties and training efficacies. For the optimization granularity, blockwise optimization, the dotted line here outperforms the layer-wise optimization for low precision, while performs similarly for the higher precision. This slide shows the result of post-processing with and without bias tuning. For different optimization variables, we can see that the dotted line, which use bias tuning, consistently outperform the solid line that without bias tuning, except for this optimizing quantization parameter case, Q parameter case here, and for higher precision, there's no differences. Based on the result of ablation study, we now construct the optimized pipeline by integrating the best option for each step. We use cross-layer equalization to pre-process the full precision model, MSE Bayesian installation to initialize the quantizers, and use block-wise optimization when doing quantization optimization, and we apply bias tuning to post-process the low-precision model. With this optimized pipeline, here we show the end-to-end result for all the models. We also vary the optimization variables for a further comparison here. And we can see that optimizing different variables perform similarly with small accuracy drop for higher precision, but there's big accuracy discrepancy for lower precision quantization. Optimized rounding is much better than optimized quantization parameters in this case. And even for the best pipeline, there's still big accuracy drop when compared to the original full precision model. In this case, it's up to 70.4% accuracy drop. If we take the best result for each model and each bit width, put them under this memory and computation saving view. Here, the x-axis is the memory saving or computation saving, and the y-axis is the accuracy drop compared to the full precision model. We use 8-bit quantization as a reference here. The lower the bit width, the more the memory and computation saving. We can see that 4-bit quantization is a sweet point that has big memory and computation saving with small accuracy drop. Some models can tolerate lower precision without any accuracy drop, but in most cases, we need to trade off the accuracy if we want to have more memory or computation savings. In conclusion, low precision quantization is very useful for tinyML use cases. PDQ is effective to achieve huge saving on memory and computation while preserving accuracy. For low precision quantization, selecting proper PDQ methods is critical to achieve good performance. And there's big accuracy gap for ultra low precision quantization, such as 2 or 3 bits compared to the original full precision model. Therefore, improving the accuracy for ultra-low precision quantization is important for future research. And there's no framework with low precision quantization support currently. Most embedded AI framework only support floating point or 8-bit quantization. As a result, developing efficient embedded AI framework with low precision quantization support will have a big impact for tinyML. That's all for my today's presentation. Thank you for listening, and I'm happy to answer any questions.
Please go ahead with your question.
Hi, thanks for the talk. I was wondering if for the, you mentioned that for the extremely low bit width, so like 2 and 3 bits, the performance drop was pretty big. Have you considered modifying the architectures to kind of relieve that degradation?
So currently, we are still based on the original architecture. We didn't modify any architecture of the original model. We want to see that, so just purely by quantization, how low bit width this kind of tinyML model can tolerate. Right, but that's a good way to improve the accuracy. And also the other one is we can for certain we did some experiments for certain layer we can increase the bit width, and then they also help on the accuracy.
Nice, thanks. Yeah, from my experience, it helps for I have some experience with binarized neural networks, And then usually we add a few more skip connections, and then you recover a lot of the accuracy by kind of improving the information flow. So yeah, maybe that could be.
Yeah, that makes sense. And another reason is that because we are purely rely on this post-training quantization, right? That means that once the model has been pre-trained, we don't retrain the model anymore. So that's another reason we are kind of not considering modifying the architecture of the original model.
Yeah, good point. Thanks.
Thank you.
Oh, yeah, thanks for your talk. I have a question. You made an interesting observation that block-wise optimization is better than layer-wise optimization for low precision. Do you have any intuition on that observation? Like why block-wise is better?
Yeah, that's a good question. So regarding that, block-wise and layer-wise optimization. So in the paper, I think in the slides, I also show that reference. That's the BlackQ paper. They have some like proof to show that for block-wise optimization, so it's kind of provide more flexibilities like inside the block. That means that the multiple layers inside the block can be optimized jointly. So that means we are not considering the optimization layer by layer, right? So that provide more flexibility for the optimization. I think that's one of the key reasons.
Okay, thank you.
Yeah, no problem. Thank you.
Yeah, I have a question. So, have you compared how this post-training quantization compares against maybe quantization hour training? Like, how much is the accuracy difference?
You mean the post-training quantization and the quantization of value training, right?
Yeah.
We haven't done this specific comparison with these tinyML models, but in general, QAT, right, usually performs better compared to PTQ. So, but the disadvantage of QAT is that it requires the original training data, right, to retrain the model. But for PTQ here, right, we only require a small amount of original training data to do this kind of calibration. So it's a very small, tiny portion of the training data. I think that's the difference. But in general, QAT perform better than QAT, than PTQ. Sorry.
Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.